Dear students, welcome you all to this video lecture. This is N. Manikandan, Assistant Professor of Physics from Government College of Engineering, Bodinaikinur. In this lecture, we are going to derive the expression for Young's modulus of a beam using non-uniform bending method and experimental procedure to determine Young's modulus. Okay, what is uniform bending method? We have discussed in the previous lecture. Now just recall that. Take beam AB and support on two knife edges. This C is the midpoint. Apply a load W at the midpoint. The beam bend like this. At the center, depression produced. The bending of the beam does not form an arc of a circle. This type of bending is known as uniform bending. Let us move to the derivation. Here we already see about this. AB is the beam, supported on two knife edges K1 and K2. Let C is the center of the beam. L is the distance between the two knife edges. Due to the application of load W, the beam bent like this. Here, due to the applied load, the force beam bent like this. The force W acting vertically downward at C. The force of reaction. The force of reaction split into two parts. In at K1 and K2, two knife edges. Split into two parts. Acting at two knife edges, each are equal to W by 2. Each are equal to W by 2. Here, look at the bend of the beam. The bend of the beam is look like two inverted cantilevers. Suppose we rotate this. See here, this is the fixed end of the cantilever. This is the free end of the cantilever. The two inverted cantilevers here. The two inverted cantilevers fixed at center C, each of length L by 2, loaded at weight W by 2. Loaded at the weight at W by at K1 and K2 W by 2. So we consider the cantilever problem. Here we consider the cantilever problem. What is the cantilever problem? We already know that. Just recall that. In cantilever problem, one end of the beam is fixed, the other end is free. We apply at the free end, we apply a load W at the free end, the beam bend like this. Here the depression Y is produced. In case of cantilever problem, this is a cantilever problem. In case of cantilever problem of length L, load W, the value of depression can be written as small y equal to WL cube divided by free YI, where Y is the Young's modulus of the material of the beam, I is the geometrical moment of inertia of the beam, L is the distance between the two knife edges, W is the applied load. Give equation number 1. Here in our cantilever, In our problem, the length of the cantilever is L by 2 and load is W by 2. Therefore, substitute L by 2 instead of L and W by 2 instead of W in equation 1, we get small y equal to W by 2 L by 2 whole cube divided by 3yi. Here 8 into 2 16, 16 into 3 48. Therefore, small y equal to WL cube divided by 48yi. Therefore, the Young's modulus of capital Y equal to WL cube divided by 48 small y to capital I. This is the expression for Young's modulus of a beam using non-uniform bending method. Here W is the applied load, W equal to mg, m is the applied mass, G is the acceleration due to gravity, L is the distance between the two knife edges, Y is the depression produced, capital I is the geometrical moment of inertia, is dependent on dimension of the beam. Special cases. 1. Suppose we take rectangular beam like this. Breadth B, thickness D. The geometrical moment of inertia of this rectangular beam is I equal to BD cube divided by 12. Equation, give equation number 3. Substitute equation 3 in equation 2, we get capital Y equal to WL cube divided by 48 BD cube divided by 12 into small y. For capital Y equal to, we simplify this equation, WL cube divided by 4BD cube into small y. Equation number 4. This is the equation. This is the expression for Young's modulus of a rectangular beam using non-uniform bending method. Suppose we take a circular beam of radius R. The geometrical moment of inertia of the circular beam is by R power 4 divided by 4. Give equation number 5. Substitute equation 5 in equation 2. We get capital Y equal to WL cube divided by 48 into pi R power 4 divided by 4 into small y. We simplify this equation, we get y equal to WL cube divided by 12 pi R power 4 into small y. Equation number 6. This is the equation for Young's modulus of a beam, circular beam, using non-uniform bending method. Okay. Let us move to the experimental procedure. In uniform bending method, experimental setup is like this. This experiment is a pin and microscope method experiment to determine the Young's modulus of the material of a beam. Already we know that this experimental setup, AB is the rectangular cross-section beam supported horizontally on the two knife edges K1 and K2. The distance between the two knife edges is L. Let O be the midpoint. A pin is fixed at the midpoint. The tip of pin is focused by the traveling microscope. The experiment, both ends, weight hanger is suspended. Now the initial reading of the traveling microscope is noted. When the load W is applied on both ends, the traveling microscope using the traveling microscope, we focus the tip of the pin. The vertical scale reading of the microscope is noted here. Here we increase the load step by step, W plus 50, W plus 100 step by step. We note the traveling microscope reading. The experiment is repeated also for decreasing load. From this tabulation, the elevation of the beam is, mean elevation value is noted. This is a rectangular beam, therefore the breadth value is measured by using vernier caliper and thickness value is measured by using screw gauge. From these values, we can easily calculate the Young's modulus value of the metal of the beam using the relation 3 by 2 mg a L cube divided by b d cube y Newton per meter square. In this equation, m is the applied mass, g is acceleration due to gravity, a is the distance, that is the distance of one of the weight hanger from the nearest knife edge. L is the distance between the two knife edges, B is the breadth of the beam, D is the thickness of the beam, Y is the elevation produced, mean elevation produced. From this relation, we can easily calculate the Young's modulus of the material of the beam. Similar to that, in non-uniform bending method, the experimental setup is here. Here, AB is the rectangular cross-section beam supported on two knife edges. The distance between the two knife edges is L. O is the midpoint. At midpoint, a weight hanger is suspended and a pin is fixed. The tip of the pin is focused by traveling microscope. Here we apply a load at the midpoint. First we apply the load W. Noted the traveling microscope reading here. We increase the load step by step. Noted the traveling microscope in reading and noted here. We also repeat the experiment for decreasing load. From this table, we can calculate the depression value Y, mean depression value Y. The breadth of the beam is measured by vernier caliper. The thickness of the beam measured by screw gauge. Using these values, using this relation capital Y equal to mg L cube by 4b t cube Y Newton per meter squared. We substitute these all values. We can easily calculate the Young's modulus of the material of the beam. This is pin and microscope method. We use pin and traveling microscope. So this is called pin and microscope method. Okay, thank you.